Well, welcome everybody to a new edition of the Ken Seminar Series, Spring 2025. Today, we are delighted to host Dr. Manny Golparvar-Fard. He's a professor of civil engineering, computer science, and technology entrepreneurship at the University of Illinois Urbana-Champaign, and serves as the chief science officer and co-founder of Reconstruct. His research advances computer vision and machine learning for construction and management of physical assets in the built environment. He holds degrees in civil engineering and computer science and has authored more than 200 publications, secured dozens of patents, and received numerous awards, including the 2025 College of Engineering Award for Excellence in Translational Research, the ASCE's Walter Haber Research Prize, and a dozen of best journal and conference papers. Reconstruct is also recognized by the World Economic Forum and was awarded for innovation in construction. So please help me welcome Dr. Golparvar-Fard.
Well, thank you very much for the introduction, and thank you very much for hosting me today. Last time I was here was exactly 17 years ago. So it brought back a lot of great memories. Like you, I've actually graduated from University of Illinois. For some of you guys who have graduated from here, I did my PhD here in civil and environmental engineering. And while I was doing my PhD, I did 95 credits hours of computer science courses. And when I came back here, they decided to accept me as an affiliate in that program too. So what I've been working on over the past roughly 2 decades is interface of computer vision and construction. There are elements of my work that's been foundational from a computer vision perspective I'm going to touch on at a very shallow level today. And a lot of my work is actually translating to a solution that's been used in the market. So I'm going to maneuver a little bit on that. And I've titled my work a little bit more industry grade on what I'm calling an AI-powered digital twin, which I'll clarify exactly what I mean by that. A lot of things I'm going to show you today have actually been used in the market. This solution I'm about to speak about that can monitor work in progress on various forms of job sites have been used on close to about 12,000 construction projects so far, all over the world. So I'll show you a few examples of how fundamental work that we did translate into a patent, and the patent ended up being acquired by the company, and the company has raised a little bit over $32 million for research funding. Feel free to stop me at any moment in time. I do have a lot of the slides, so I want to gauge your interest in different topics. We can go deep, or we can quickly go over various topics that I'm going to be presenting to you today. So what you're going to be hearing about is a little bit of my own personal journey of how I've tried to balance what I do on campus versus what I kind of explore at my company and my team does at the same time. Before I get into the technical content, I want to give you a little bit of perspective on the industry. Last few years, the world of construction has gone through a lot of changes, but the value put in place continues to grow. In fact, 2025, this is probably going to be the highest amount of money that we've ever spent in construction. How many of you guys have been hearing about the tariffs? A lot of you, right? So I'm guessing everyone is hearing. Despite everything you're hearing in the news, our forecast from an AIA shows that we are expecting 2% real growth in construction. So that number is actually really, really exciting. So if you're graduating this year, there's a lot of job opportunities in construction. But if you look into this money, a big portion of it goes into the labor. By labor, I'm not just referring to the workers that we have on the job site. I mean, you and I, everyone who's engaged in the design process, people who are engaged in the managing of the pre-construction process, all the way to the operation. Every project that we engaged in has many different companies. If you pick an extension that is happening, for example, to a building on campus, you probably have about 20 to 30 different subcontractors that are working on that job site. So a lot of people that are involved in engineering and management of construction, they have to spend their time coordinating and communicating who should do what work in each area. And there's a lot of waste in that process. That waste is roughly around 35% of the time. Now, if you do the math, 35% times 40% times roughly $2.2 trillion, opportunity for addressing just the coordination and communication issue in construction is roughly around $300 billion. Any football fans here? Any American football fans? A few. All right. What is the biggest stadium that you've seen lately? A new one that's been done. SoFi Stadium, right? Does anyone know how much was the construction cost for that project? $5 billion. It was estimated at 2.2. It was finished at 5. So a little bit over twice as much money, right? But if we address this problem, every single year we can go ahead and add another 60 SoFi stadiums for you every single year. Just want to make sure that we understand the order of magnitude of the problem that we have in construction, even in 2025 with coordination. Make sure that this thing is working. But I want to give you an example of what it really means for people engaged in construction. That means, unfortunately, on every 2 commercial projects that you see on average, one of them is behind the schedule. Does anyone know any project that's actually been finished on schedule or ahead of a schedule? Anyone? Well, I don't want to get into IDOT projects, but you get my point that I'm trying to make, because of so many problems that we have that typically happens in construction. Now, when you look into larger projects, projects that are larger than $500 million in size, where coordination is a bigger issue because we have more people, the likelihood of cost overrun and delays is dramatic. If you look into every one of these projects, it's really, really large. I want to put this into an order of magnitude for a client that I've had the opportunity of working with. How many of you guys are using Facebook or Instagram? All right, so the owner of that company, Meta. Does anyone know how many projects Meta does a year? So the biggest construction projects that Meta or Facebook does are data centers. Today, there are 12 data centers that are actively under construction by Meta. Each of these projects is roughly around $500 million to $1 billion. Let's take the lower number. How fast do you want to have the data center to be completed? 8 to 10 months from the time that you started, because nobody wants to wait for their picture to be uploaded into Facebook. You want to have that done instantly, right? You get the picture that I'm trying to paint for you. Every single day, Meta does $60 million of work. $60 million of work a day. Before 5 p.m., that's how much money that we spend on construction. So you can see how this coordination issue and how keeping their projects on time can make a huge impact on work in progress. Now, many of you guys have transportation background, and some of this might be relevant to you, but if you don't, I'm basically giving you a little bit of glimpse of what happens in construction. Every project that we do always starts with a plan. We go and execute that plan, and from time to time, we check to see if we can compare what really happens out in the field against that plan and make adjustment. Now, over the years, we've added new theories in construction. One of them is what we call last planner. Anyone who's been on the job site might have heard the term pool planning. It's a practice of bringing a foreman to a meeting. That's the better ring of planning and execution that you see on the side. But the gist of it is, all we are trying to do is to understand how we can find the delta between reality versus the plan and make adjustments. Within this workflow, there are 4 specific problems of why projects are falling behind the schedule. Number one, like I said, over the past few decades, the broader scientific community in construction worked on a number of theories called last planner, which the idea was really, really simple. Instead of running a team by having someone come up with a schedule, ask the people who execute the task to give you the estimate of how much work needs to be done. What really happens is you take a team that does, for average of, let's say, 1,500 to 2,000 activity in the life of a project, to a process where now you do 20,000 activities. That you need to coordinate who does what work in each location. Every one of these sticky notes you see is actually one card that shows you one company doing one task a day. And that's the practice that we have. When you want to be coordinating this much work, you need to have someone as a champion on the job site to guarantee and communicate the work that needs to be done. In the absence of these champions, people go back to the practices that we have day to day, that we get together in a weekly meeting and we reflect on our past. How many of you guys go to weekly research meetings? If you've not been communicating to your advisors, you know what's going to happen? If you've been delayed, you're going to get a reaction on that delay, right? That's exactly what happens in construction. So not only, again, I'm just making fun so I can engage in conversation with me. Not only we are not necessarily good in planning, but when it comes to executing our plans, there's a lot of room for improvement. Over the past 15 years, I've been surveying every superintendent that exists in construction on why things are not working according to the plan. And they give us feedback on all sorts of things. They show up, the work plan has changed because the project manager decided to do some different approach to project. You show up, another subcontractor has occupied your space. Resources might not be available to you. If you look into these reasons, almost 80% of these issues are preventable. The problem is all of our projects are understaffed. So people that are on the job site, they don't get visibility to what's really happening on the job site to be able to react to it in a timely fashion. Third problem, the way we monitor construction progress on job sites. How many of you guys have actually walked into a trailer, seen a piece of 2D drawing on a wall that's been color-coded? Anyone here? All right, that's the first thing you're going to see if ever walk into a job site. Now, I say modern EV plant. I know this is being recorded, but my understanding is being recorded for affiliates of our program. This is a Ford facility in Michigan. It's an EV plant. It's a very modern plant, which plans to build the type of vehicles that you do research on, but looking to the construction practices. This is the same that they've been doing since 80s. You wait for the entire week, contractors show up in the room, and you ask them to color code what are the areas that they've been working on. So from the time that the problem happens to the time that you get visibility to it, you've effectively lost 1 week of time. The last problem, not only we have problems with the way we plan and execute and we monitor it, we actually don't even use that data to update the plan. The people who are engaged in the process of planning are usually not even on the job site. So they're always missing that feedback loop of how much work really happened on the job site and use that as a basis of updating that plan. Now we call that engineering judgment, but it's really gut feeling of how much I think everyone can do on the job site. So I can come up with that plan. So again, there are 4 specific problems: the way we plan it, the way we execute it, the way we monitor it, and the way we use that data to update it. So we put ourselves on the path of solving these problems with only one form of data. A type of data that if you put it in front of a superintendent, if you put it in front of an owner, you put it in front of a designer, everyone understands how much work has been done, and you can contrast it against your design. And that form factor of data is visual data. So what do I mean by that? If you ever come across job sites, you're going to see people taking photos. Most dominant form of taking pictures is using a phone, walking around job site and taking pictures. How many of you guys have actually used your phone to take a picture of a job site or visit that you had? All of us, right? That's the same in construction. For liability reasons, many owners in the US and overseas, they hire professional photographers that would actually walk on the job site and they take photos for you. Any guesses of how much money these guys are making on an hour basis? Pick a number. Go up. How much do we make as GRAs? 20, 30 bucks, right? So let's have a benchmark. We pay $200 an hour for the professional photographers that are showing up on the job site to take photos for liability reasons, okay? It's a good opportunity for this summer. We also have time-lapse photography. Many of our job sites have fixed cameras, and we also use them in transportation projects. Superintendents love to use action cameras. These are 360 cameras you can easily place over your hard hat, walk around and videotape. Construction is the #1 market for drones. It's larger than agriculture. It's larger than transportation. And we use a device called laser scanning that you also use in transportation. This is less frequently used, mostly for high precision tasks, but these are different forms of visual data. So what we wanted to do is to see how we can take this data and use that to represent what really happens on the job site, and then use that to communicate what work is coming up. So on the other side of it, we had to look into what we can bring from a design perspective. Over the past 2 decades, we've advanced a concept called building information modeling. I'm going to show you some of those examples in the world of transportation. It's not very dominant in the world of transportation because conflict resolution in engineering doesn't take as much effort as building does. So it creates more value from a building perspective. But again, it's something that people explore in the world of transportation too. The idea is very simple. You take that design model, you take a project schedule, you integrate them so you can create a sequence of the work. And before the job starts, you can use that to coordinate and communicate what work is coming up. And over time, you can use that for constructability reviews, safety reviews, and so on. I want to give you an example. I try to bring as many transportation examples as possible. This is Oak Ridge Bay in California. You can actually see what Caltrans together with AECOM had done at the time. Over here, you can actually see the animation of construction, and you can also see active traffic. We actually do use data from traffic engineering estimates that are done to kind of understand how we can make the job site safe during construction and look into constructability. And on the other side of it, of course, you can see the reality. So the idea is to see how we can bring this animation and visual data over time into the same scene. And here's the idea that we put together. We thought, what if we come up with a technique that first and foremost can make every picture measurable? So we can click on this picture and say, you know what, I want to see the length from this safety cone to the other safety cone. 2, we wanted to see if we can automatically bring design as an overlay on top of the picture. 3, have a schedule tied against that model. So at any moment in time, you see what is being planned on the job site against the reality of the site, and any deviation between the 2 of them would be color-coded. What do you guys see? Areas that are color-coded in red. Maybe those are areas that are behind the schedule. So when we go into the coordination meeting, everyone is on the same page of what work was promised, how much work has really happened on the job site. Any questions so far? All right. Now I want to take you back to what I mentioned before. You remember the cycle that I showed you about planning, executing, monitoring, and controlling? This is the same cycle. If I can bring design plus a schedule, which now we call it 4D BIM, fourth dimension being time, I can go ahead and use that as a base of reliable planning. If I can figure out a way that I can make my pictures measurable over time, I can generate a reality model of the job site that can capture what really, really happens in a measurable way on the job site. Then I can go ahead and twin that against the design at a high frequency. Two requirements for definition of digital twin. The fact that it's one, digital representation of actual job site. Two, it comes at a frequency, right? So I can go ahead and tie the two of them together to better coordinate and communicate what work needs to be done. Then I can, apply to more advanced analytics, and I can find the delta, and maybe I can forecast the future. So this is the idea that we had, and basically transforming the cycle of project controls to something that's driven by computer vision. Fast forward to today, we've actually expanded this capability, and it works with every device in the market. I just wanted to show you the most dominant hardware. My work never gets into a world of hardware, but this is what we have to interface with. 360 cameras, people love to use them because they're really easy to use. Drones, even though we have a lot of regulatory requirements around drones, still very heavily used for larger scale. We love to tap into videos from phones, not the LiDAR, because not everyone on the job site has that LiDAR. And of course, on the more extreme side of it, if you guys have rented any apartment in Champaign, you might have had a virtual tour. This is that device that gets used for that. And of course, laser scanning. So essentially, regardless of how pictures and videos are being taken, we would create a time machine for you that would be measurable. Now, you would never find a job site that would only use one form of this visual data. There's always at least two forms of them used at the same time by different trades that you have. Let me see if I can advance this slide here. All right, so what is the idea? I'll get into some of the details at a later time. The idea is that from that collection of photographs and videos that we're capturing, at any moment in time, we want to see if we can generate a three-dimensional model of the job site. This model you see on the screen is called a three-dimensional point cloud, a cloud of three-dimensional points. What we want to do is we also want to put that on a timeline slider. So these orange dots you see down on the timeline, each of them will be one day that the team on the job site is taking photos or they're capturing videos of the job site. This project is actually Centene Tower in St. Louis. This is a project that's already completed, and Clayco Construction used this technology throughout the project. Once we achieve that, we want to go ahead and bring that design at whatever level of abstraction that you have. Okay, then we're going to go ahead and tie that against the schedule. So at any moment in time, now you see what is being planned, which we call it as planned conditions, against the reality of the job site, which is the as-built condition. And then we want to see how we can twin them against one another in the same coordinate system, right? So now everything will be sitting in the same coordinate system. Because that point cloud model has been generated from photographs, we can go ahead and back project the design on every photograph based on mathematical formulation that I'm going to show you in a moment. And that means now your design plus the schedule will be overlaid. But from a contractor's perspective, you show up at the job site, this is on a large monitor, you say, hey, let me see what are the companies that are going to be working on my site today. We have Concrete Strategies, we have Harman. The model carries the quantity of expected work. The visual in the background shows you the actual quantity, so you can start measuring real work against expected work and do that coordination issue better and better. Over time, I can start color coding. I can color code locations. I can color code work packages. I can color code contractors that are on the schedule and behind the schedule. So for example, you see the podium deck in this case color coded in red for areas that are behind, and some areas might be on schedule. You may want to let that chestnut in. Thank you. Down here, you can actually see the schedule. So again, it shows you the timeline from the reality perspective against the design. Now, if you can also start tracking performance in terms of production and even better productivity, maybe we can forecast the future. Now, we are not in the business of forecasting all types of risks that can happen on the job site. This needs to be something that's realistic. So all we are trying to do here is we are taking the data over the past 3 to 6 weeks on the job site in terms of how much work has been done. And we are only forecasting in the next 3 to 6 weeks on locations that we're thinking that are likely going to fall behind the schedule. Okay, so I'm going to use my words again carefully. Locations that are likely going to be falling behind the schedule. So we can color code and say, you know what, when you go into the coordination meeting, you should focus on that location because you're likely not going to be able to get your tasks started on time. So I want to take you back to the basics of construction. This is what it means. You put it in front of a group of people. The system is highlighting two locations that are color-coded for risk, red and yellow. And everyone in this meeting is having a conversation around what are the areas that are at risk, what tasks do I have that relate to that location, and how can I be part of this collaborative discussion on revising the plan so we can prevent a delay from happening as opposed to reacting to it. Okay. Now, putting that sophisticated concept aside, we always jokingly say everybody's paying attention except the fellow who's on the laptop or tablet on the lower right corner, right? It's visual. It catches the attention of everyone, obviously part of a coordination meeting. Any questions so far? Now, this is at a high level what the idea is. So now wearing a little bit of academic hat, now you may say, all right, so what is the exact process? What is the underlying science that actually generates this type of technology? And what is the mechanism of going from a group of pictures into a three-dimensional model against the design model, right? So, fundamentally, I want to take you back to the photo that I showed you before. How would you align a three-dimensional model against this picture? Not only you need to do this per individual picture, but you also need to repeat that for every one of the photographs you have on the job site. So this is the task, provided with a group of pictures, a 3D model. Any ideas? All right, so you may argue and saying, yeah, you know what? What if you put a GPS tag against this picture, right? What kind of tolerances do you get from GPS, right? Given the line of sight, for those of you who've done staking in transportation or you've done surveying, you can imagine it creates a deviation against it. So GPS is not available on a lot of our videos and images on the job site for all kinds of reasons. Two, if you want to make an alignment, you can argue that I'm looking for a number of visual features and I'm going to go ahead and align them against the design. But what is it that we do in design? I'm looking at you guys because most of you guys have been in the world of design. Design is an abstraction of the real world. What we present in design doesn't match the reality of the job site. So we need to figure out a way that we can define features from that world, from a computer vision perspective, that would actually match mathematical description that we would put into features from a visual perspective. Now, I want to mention this a little bit more from a computer vision perspective. In computer vision, we take every image and we use different types of camera models to model them. One popular model is called a pinhole camera model. Each and every one of these images would have a few characteristics that we need to learn about. One, we need to understand the focal length. We need to understand the skew. That means what kind of shear we get from the video. We need to understand the geometry of the optic center. At the same time, we need to understand extrinsic parameters that are dominantly rotation and translation of the image against some coordinate system. So you're looking at 11 degrees of freedom. Does anyone know how many points we need to solve mapping between 2D and 3D against 11 degrees of freedom? Any guesses? Well, each point is going to give you X and Y. So 6 times 2 would be 12. So we need a minimum of 6 points, but I need to find these points for every one of these images, knowing that that abstraction of the design would not help me match. So we thought, okay, well, this might be a very difficult problem for us to solve, but let's look into it from a different perspective. These images, we have so many of them that naturally they have an overlap against one another. What if we try to understand the structure of the scene from the motion between these images that can be modeled, a science called structure from motion? So now I'm going to generate a three-dimensional representation of the site, not because I need that visual, because it actually glues all my cameras against the same coordinate system. So every one of those prisms or frustai that you see up on the screen would be one of the locations of my images. Now this problem would be 11 degrees of freedom per image, but you also have 3 degrees of freedom per point X, Y, Z that we need to map in the scene. Fast forward, we have about half a dozen of publications that over the years that we published on this. That was actually the first IP that we brought into the technology. This is how it works. You provide a group of pictures into the system. It goes into a number of steps of a standard structure for motion pipeline. We change the algorithms that people use in the world of 3D reconstruction to densify it by making the compute time to be linear. And we added a number of meshing capabilities to fill in some of the holes that we have. So this is the real life experience that you're going to get if you put it on a web-based viewer. And the idea is that you have the 3D model. You can click on any location. With some computer graphics algorithm, you can actually overlay the image on top of it in a memory efficient way. And now in the moment that you see this fellow is putting up the measurement tool, and every point in the measure becomes, every pixel in the image becomes measurable. So I can solve this problem. I need to figure out how I can align this over time. Look at the date, April 21st. Every one of these orange dots you see on the timeline would be one of my capture days. And I'll show you what the trick is on getting these aligned. But we actually came up with an algorithm that depending on how much of the site is being captured. We look into the past history of the site as a dictionary, and we see if we can find the same type of features over and over. And over time, we generate what we call a four-dimensional reality of a job site. Okay. Now, some of you guys may be using computer vision algorithms in your work. We've actually changed our bound adjustment process, and we're constraining every reconstruction against the one that we had from last week. That's the easy trick. Now, there are moments that the site drastically changes in terms of progress, and the algorithm fails. That's fine. You come with an interface that the user can go back and fix the alignment over and over. Now, here's the next piece. We need to figure out how we can go ahead and do the alignment. Now, over time, we've come up with many different algorithms to do this alignment, but I want to take you back to some of the fundamentals that we use in civil engineering. We love to do everything based on control points. That's what we do in transportation. That's what we do in construction. The idea is that you define a number of control points in your design and a number of control points in the real world. And all we need is to solve for the similarity transformation that only has 5 degrees of freedom. That means only 3 points. As long as you get 3 control points, you can go ahead and transform your unknown coordinate system into your design coordinate system. Now, I jokingly say we usually don't have these problems in transportation, but today I want to confess that's true, because in the world of transportation, your design is dominantly based on real coordinate system. Everyone who works on non-transportation projects are always in some arbitrary coordinate system, regardless of whatever we try to do on execution planning. So we've come up with a number of algorithms that can facilitate this process for things that are not based on site coordinate system. What it does is that now it brings your design into the same coordinate system. And you remember the photographs are part of the point cloud. I've turned the point cloud off. Now it's all part of the same coordinate system. These are where images are located. That's your 3D model. So you simply back project that 3D model onto the image, and you get those views that I was showing you before. All right, so that's basically the trick behind getting this to work. So back in 2014, 2015, we kind of brought a lot of these algorithms into maturity. Gosh, now it's almost 10 years. And we started putting into practice. Many of these practices were prior to FAA Section 107 and Exemption 333. That meant we did not need to hire any pilot to operate it. And we started testing it at scale. We actually did 126 captures with the first iteration of the more mature algorithm, from Sacramento Kings Stadium projects to projects on our own campus, to projects in Chicago, Miami. That project is actually with Taisei Corporation in Japan. This is one of our donors on campus, W. O'Neill. And immediately we learned that, okay, so although we've brought some of these computer vision algorithms into the practice of the built environment, there are a few issues that we're facing. One, there's never any guarantee that the models that we generate is going to be complete, and you would get these holes in the model that become questionable and can even challenge your auto alignment practices. Two, because you're working on a numerical optimization process, you may always get into, your algorithm may get stuck in local minima, and because of that, you may have a drift. And this drift varies based on capture practices that we have, but right angles may not be preserved, which is a big issue for us in construction. And the third issue, remember I said images, they don't have any coordinates associated to them, they don't have any GPS. So the models that we're creating are up to scale. That means on their own, they're not measurable. You need to offer reference to fix that issue. So that was a moment in time that we realized, okay, everything in the world of construction starts with the design. What if we go back and take our concept of design into the world of computer vision and transform the way we think about image-based 3D reconstruction and use that design to assist that process? That was the question I wanted to ask. By the way, this is something that we published at CGraph, a dominant computer vision, computer graphics venue. So the idea was very simple. You remember we used to do the BIM alignment post-reconstruction, right? We reversed the question. We said, what if upon initiation of the project, we looked into solving the alignment problem using a perspective endpoint algorithm? That means I need a number of points between my 3D model and only one single picture. And I'm going to go ahead and solve through this formulation I'm showing you on the screen to bring that design into alignment against the picture. Let's see what happens. I'm basically going to use a user-guided input, and I bring the design into alignment, and I'm going to go in and treat this image as an anchor image against the rest of the photographs that I have. Does anyone recognize the building I have on the screen? This is EC. So this is the time that EC was going on the construction, and we actually did the testing on campus. So basically, here's the idea. In that bounded adjustment process, and again, I haven't gone into a whole lot of detail. I'm only showing you a snapshot of one of the algorithms here. The image that has been associated with the 3D becomes an anchor. And we use that as a constraint to make sure that when we're trying to optimize, we keep that fixed and we only rotate and translate the rest of the scene against my anchor point. So this is what that process would look like if you want to expedite it. You solve for feature track generation process, you anchor that image. Because your features have already created tracks against one another, you simply transfer them into the next image, use the same PNP, you place the bit model on the next image, and so on. This process can be actually done within a few minutes, so we can automatically figure out what are the images that may not immediately get registered. So we provide that again as a feedback to the user. The user provides that fix for us on that model. Funny, you see this image that did not align is the exact same view as the one I'm showing on the left. Can anyone guess why? There's more progress made in that photograph, right? So the visual representation of our feature descriptors are totally different. And for those of you guys may not know, basically what we are trying to do is we capture changes of color intensity or changes of brightness intensity within a set of neighborhood in a 128-dimensional vector. That's all we learn. And it needs to be fast enough that we can do this for every image. And you have roughly a few thousands of these features per image. So again, you provide as the input and that anchors it. Now we realized that for the first time, we've actually taken a concept from the world of civil engineering to computer vision. And if you want to publish it, we cannot publish it with our own data set, which we would have loved to do it. We have to go back and benchmarking what is commonly available in the world of computer vision. Now, this is a data set of dinosaurs and temples and all that people use in the world of graphics. People have mock-up models and they love to bring them into movies. So they actually scan them and they compare algorithms against one another. So as you can see, the two metrics that we use is to figure out how we can minimize our localization problem, which is minimizing the placement of the image in 3D by measuring our translation error and rotation error. Now, this system that we benchmarked against was based on a paper from University of Washington, visual tour. And that was the basis of Microsoft PhotoSynth. So at the time, benchmark was PhotoSynth system. So again, we display that this improves it. But for us, again, I want to bring it back to what our problem was. Our problem, you remember the drift I was showing you moments ago? You can actually see what that drift would look like if you use that standard structure for motion process. But if you constrain that against the design, you can go ahead and improve that. And likelihood of that would go down. And because you're using that constraint, our 3D reconstruction is likely going to give you a more complete picture of the scene, as opposed to what typically happens with any standard structure for motion process. All right, now I want to take you back to a slightly higher level. So I only showed you one workflow so far, which is taking a group of photos and videos and putting them into a system to generate that time machine for construction. Fast forward, I want to show you the solution that has become commercially available. The company is owned by University of Illinois. So if I'm advertising, it's because university owns it. And there are three capabilities here. You can bring your photos on their own, use them to document both condition assessment and construction progress on the job site. You can bring your design, both 3D and 2D, and you can also bring the schedule. The entire interface is web-based by design. So you have less memory to use and less GPU to use for rendering purposes. And of course, there's a number of mobile interfaces that helps you go back and forth between different users. We've used this with many, many different partners and many, many different companies. Our biggest partners that have been helping us on selling are the dominant companies that you know from the world of design. For those of you who may have some interface with the world of insurance, there's a lot of application of what I'm showing you for insurance world, specifically subcontractor default insurance, meaning you insure yourself against subcontractor going bankrupt. So that's why we have that partner, Aon. And over here, I'm just showing you select companies so I can show you examples of rail projects that we worked on, data center projects that we worked on, hospital projects, and some unique job sites that are more on the theme parks. The ones that I'm mostly excited about these days are the projects that we engage in Saudi Arabia. I've had the opportunity of traveling to these job sites. These are all designs. That's not the reality of what's going on there right now. This is the line that I know many of you are probably very interested in. This is the Walt, which is the gateway for this project called Trojena, which is a ski resort in Saudi Arabia. And that's the place that the 2029 Winter Games for Asia would be hosted. And this is a floating city called Oxagon, all in the Red Sea area. So some examples of these projects. So fast forward, this is how exactly the solution works. The most dominant forms of captures that we've seen are the drones, 360 cameras, and this is actually something that we came up with. This is a time-lapse camera, this is solar powered. You put it on a tower crane. If you can't use a drone, every single day, the tower moves about the job. We put it on a trolley, so it naturally takes time-lapse photos. You put it into the system, it generates a measurable model. Now you can go ahead and overlay it. This is actually headquartered of one of our customers, Hewitt Construction, that he uses this technology on. Here's another example of showing this at scale. This is a Microsoft campus in California. The owner rep is a company called OAC Services out of Seattle. They want to have visibility of what's going on the job site. So you can see the density of the captures. Almost every other day, they were actually doing a drone capture on this site. So the idea that they had was to have remote visibility of what's happening down in California so they can expedite payments for the contractors. That's another big issue that we have in the world of construction. But simply, as you can see, there are 18 buildings on this campus. You click on a location, the capture that you have with the drone will be transformed into a measurable experience. And you can obviously see that on what I have on the screen here. All right. In early days, our most dominant form of capture was drone. And drone was automating the capture, but every few years that you put things into the practice, people want to have something that's easier, cheaper, faster to use. These 360 cameras came out. These are the ones that we place them on the hard hat. How many of you guys actually have 360 cameras or use them? Anyone? All right, maybe some of you. All right. If you ever walk on the job site, I can guarantee almost 8 out of 10 projects that you visit would actually have these cameras today. They're really, really popular. You put them on your hard hat, you walk around, it captures what's in front of you, left, right, top, bottom in one walk, right? So it minimizes time and cost for FTE. Your full-time employee doesn't need to spend time doing a lot of capture. And plus, in indoor environments, a lot of safety managers on job sites would not allow you to fly drones for 2 reasons. One, of course, you don't have GPS to navigate the drone, autonomous or even manually in the job site. 2, drones have magnetometers. When you keep the drone close to a steel structure, which is something you see a lot on job sites, it would actually throw off your navigation system altogether. So it's very likely that would have an accident on the job site. So again, this became very popular. What we've done with it is we've extended these algorithms and we take the video feed from these devices and we automatically generate the point cloud as before. We offer walkthrough experience, but we also map that in 2D. So we can actually generate an ortho photo that we call an as-built floor plan, and that can be matched against a 2D design too. So I'm going to give you a little bit of a quick demo of what this experience would look like. For those of you who've used Zillow or you've used maybe Apartment Finder, you are familiar with this experience. The difference is those experiences are created by these devices that are placed on a tripod. Each scan is 19 seconds, so it takes a lot of money and time to do the capture. Here, you're just cruising through the site by walking around. This is the floor plan that the video is automatically generated. The donuts are frames that are selectively extracted from the frame. You click and you navigate from point A to point B. Image is entirely measurable, so you can measure your drain pipe against the joint that you see over here. And there are all kinds of measurements. You can teleport yourself from point A to point B. The date is shown at the bottom of the screen, 2020. Location is level 16. This is actually a project in the country of Netherlands that the contractor Volker Vessels was actually using the system. You can also switch to 2D, and I'll get into this piece in just a moment of how, but basically now you can actually see your walkthrough path against that 2D environment, and you can kind of see the site and do the same type of overlays I was showing you moments ago. Now, as we started scaling this technology, we realized that many projects, while the design starts from 3D, when it comes to construction documentation, they go back to the world of 2D. 2D are the most definitive views that we have from a design perspective, and from an engineering perspective, we put a stamp on it. So now we had to worry about how do we make the system work purely based on 2D without 3D systems. And I'm just showing an example of another project and I'll explain how the process works. Here's a point cloud generated from a 360 camera walkthrough, and it's mapped against 2D. And this is actually McDonald's store. McDonald's is another company that's been using our system on their job sites. When you show this point cloud to users that you have on a job site, they feel like they're looking at a pixelated image. This is where your design of system comes into the play. So we've actually changed this interface, and we basically offer them the same street view experience that is very common in the world of transportation, but now for the world of buildings. You stay in the image, you do your measurements here, you click on the donuts, and you can walk around. And if you remove that image, basically this is what's happening. You can contrast between the image versus the point cloud, again, all geo-registered against the 2D drawing. Now, the basis of the algorithm behind it is really, really simple. When we generate a point cloud, we actually project it in the world of 2D. Then we actually perform a very simple set of feature detection. Our features are edges, points, and blobs, and we like to get a lot of those. And what we try to do is we want to see if we can fit a model that would transform your 2D design or the camera path that is shown with colors against that 2D. And we actually use a model fitting algorithm for that to prune out any bad matches that we may have. And of course, we have a nonlinear process to refine that process. But I want to give you the reality of what happens. This algorithm would only be successful if the reality of the job set matches the design. Remember that comment I made before? So many, many times in practice, this fails. But you go back and you manually fix it, and the customer keeps using this on the job site. So that's actually a project in DF Illinois. This project is in Manila, Philippines. A Japanese company called Shimizu has been working on it. This is actually a recent capture. So immediately when you bring the world of design and construction, there are a few ideas that pops in the head of people who are in the world of construction. They say, can you help me identify my quality issues on the job site? Now, one of the theories that we've been working on in the world of construction is BIM-driven design coordination, which is meant to minimize rework items that happen on the job site. But in practice, even though you do that coordination, people show up and they do their installation based on their understanding of the design. So here's an example. Here's a hospital facility in Virginia. The design was dictating that the HVAC would have a riser and sprinkler system would go under. But see what's happening? Subcontractors showed up, installed one straight piece. So now the system is flagging that location as a location that is potentially a conflict, so you can minimize the likelihood of this growing to a litigation issue. Here's another example, concrete placement. This one is very common. Every job site has concrete placement, so people want to do quality control on that front. Here, the idea is that you would use your smartphone. That's a form factor of the capture we recommend because everybody's carrying a camera. You walk against the rebar cage prior to placement of concrete. Usually takes about 30 minutes of compute time on the cloud, 30 minutes. That's the optimal number that we have in mind. And we can give you visuals that would display the design over reality. This is the same healthcare facility I was showing you moments ago. These are sleeves. For those of you guys may not know it, basically these are openings that we create on the floor to route our mechanical electrical systems in it. This is the healthcare facility. That means if you don't catch these deviations, you place concrete and you come back and what do? You bring your drilling device and you start drilling through concrete. Does anyone know how much any of these sleeves would cost? Make a guess. $2,000, $2,500 each. There's also a penalty of damaging integrity of the structure, $10,000. Right here, you have a $17,000 rework item that can be caused simply by overlaying design against reality. This is unfortunately very, very common in Illinois. Box out, sleeves, conduits. A lot of contractors in Chicago like to have the ability of doing it. This is a byproduct of what we created, but we learned that from practice that this is something that people love to do. They want to check quality of their work, especially if it's lump sum contract, for those of you who understand contracting too. Now, oftentimes I get asked, are DOTs also using it? As of now, 2 DOTs have actually scaled. There are a number of other DOTs that have been using. This is PennDOT, which they've actually publicly presented both of these projects, and hence I'm showing on the screen. This is New York Department of Transportation. Their use cases are slightly different. PennDOT is heavily interested in aerial mapping as opposed to ground-based. New York is totally different game. They actually want to do ground-based because they don't want to get into the headache of legal issues associated with flying a drone. Here, it's a simpler process. Here, sometimes they place these 360 cameras on ATVs and vehicles, and they cruise through the job site to do the capture. Our algorithm doesn't work that way. We only take 1 frame or 2 frames out of every second of capture. So we have to fine-tune these algorithms to make it cost-effective. It's just engineering. There's no science behind it. Engineering the solution in the sense that we can make it scalable. What are the other examples from the world of transportation? Here's another one for you. This is Melbourne tunnel inspection process. For tunnel, you obviously need higher precision, but we're able to place control points here and guide them to this process of commissioning. You see a deviation between the piping that's been done here in the scene. This is not a construction problem. All you need to do is you go back to the design and at the end of the day, update the design to make sure it's been updated for the reality of the job site. Here's another recent example. This is one of the NEOM projects that I can publicly show. This is the one that was actually opened about 3 or 4 months ago in Sindalah Island. The project I'm about to show you is right over here. This is the Marriott Hotel. If you look into the footprint from a linear perspective, you're looking at about 800 feet. So this is probably a hotel at the size of one of the places that you might have visited in Vegas. So just imagine the size of this. Here's the challenge that they had. They had hired AECOM design firm to walk around the job site and perform an inspection on sprinkler heads. Let me remove the audio on this and I'll play it. And the count was inconsistent against the design. The site happens to be about 2 hours away from the engineering camp. And there was a pressure of getting this work done. So they decided to go inside and videotape it and sit down and manually inspect every one of these sprinkler heads to make sure they're actually satisfying safety requirements of getting this project open. So over here, you see a little bit over 980 sprinkler heads were inspected. And the color coding here is some of them are deviated, some of them are damaged, some of them are. So there's a defect detection capability that was actually deployed here on this job. Now I want to show you a few more examples on the construction progress tracking piece of it. This is a project in Florida. This is Broward County Convention Center. It's a development site. It's been going on for about 5 years now, and this is phase 2 of that site in about 2020. And the idea was that the owner rep wanted to have a risk assessment capability on his schedule. So they took these pictures, they brought the design model, they tied that against his schedule, overlay, and over time getting color coding capabilities done. These capabilities have been used beyond our initial intent of progress tracking, specifically for payment. This is actually that Microsoft job site. So the idea here is you compare the design, you get a payment application from the contractor that tells you how much money they're going to be charging, and you can do a back of napkin calculation in terms of whether these numbers make sense and expedite that payment. Now you may say, are these 4D and these progress monitoring capabilities really scaled to the world of transportation? I want to give you a snapshot of the reality. Now, oftentimes when we are in looking to this from an academic perspective, we work with the 1% of the 1% of the market, the first adopters. But this is PennDOT, a really forward-thinking DOT, and you can kind of see, hey, you know, our level of readiness on 4D is literally what you see on the screen. This is 2020, and at best, their 4D is putting a few boxes to kind of communicate the idea of sequencing. And I want to bring you back to one reality that when you want to bring a technology into the practice, you always have to think about what is it that these guys can really, really use, and just taking one step at a time. You cannot take people from today's practices to something that's completely automated. You need to have this journey for the user to figure out how they can start ripping off values from various systems. Now, on the more extreme side of it, I want to take you to Manila. This is a former graduate of our own program, Mitso, who's now the project manager on this job site. And down here, you can actually see the schedule that Shimizu put together. You see the reality on the top. And here's the color coding of the model overlaid on top of it. I'm happy to see Professor Errol here. This is something that you might be of interested. They actually mapped out different layers for tunneling with colors. You have to help me understand what it is, but basically you see the 2D, you have the color coding, and they're actually looking to it in terms of the actual progress. I'm guessing the TBM machine was being adjusted based on the layers that are discovering on this site. So again, some other use cases that we did not think about in early days. Now, everything I've shown you is visual, but because they're actual quantities against expected quantities, you can start tracking progress and productivity. These are real production charts for self-performing works, which are down here, concrete rebar, formwork. So that actually shows you the rate of the work against what was planned. For the first time, we actually have data that we can use to update plans. And on the top, you can actually see examples of work packages that subcontractors are performing. Anyone from Latin America may recognize this company, Proicon. This is in, I'm forgetting where it is. I don't think it's in Mexico. It's in, anyway, it's in one of the Central American countries. Basically, over here, you have a health of a schedule that they wanted to track. You see how many tasks are being allocated, how many of them are getting done, so you can start generating these dashboards. And now this is bringing it back into the practice. When you have the visual data, when you have the reports based on the actual data, you can put it in front of the people. And that practice that we're only reflecting about the past, it's all proactive. You show the future of the project is coming up in the next few weeks, and this fellow works for the contractor that's placing concrete. He has all the incentives in the world to be part of this conversation, help maximize productivity of the job as much as it does on their end. We actually did a little bit over 18 months of research on this, and we published this. It's really rare for us to have data that is actually captured on a longer time period. So we are proud of this, that we are able to take these guys from getting roughly 50% of the tasks done on a weekly basis to roughly 70%. 80% is really good. I don't want to speak about our own research experience, but imagine your advisor giving you 10 tasks. If you can do 7 or 8 of them, you're already on a high mark, right? So that's the same idea here on the job site. And we're able to minimize the number of times that somebody shows up and says, you know what, I need to do that again this week. And you bring that task over and over. So the same type of metrics that we use in construction. I want to just quickly touch on a few questions that probably you have. One is, oh, what about automated progress tracking? Our intellectual property for this technology is entirely on automated detection. Oh, my formulation for some reason changed, but I'm not going to cover the formula anyway. This is something that we patented and we acquired the patent to the company. This is our first idea that we published in ICCV and CVPR, which are computer vision events. The idea was, because we track progress and we have a geometry understanding of the scene, maybe we can reason about occupancy and visibility of the scene, both from an image perspective and a design perspective, and we can map that in a probabilistic form and feed it into a very simple machine learning algorithm that can detect if an object is on a job site or not. And over time, we realized that our system, purely based on geometry, can make a lot of mistakes. Here's a false positive. What do you guys see highlighted here? Do you see formwork? The system thought that this is concrete. You see it color-coded in green because he wasn't able to differentiate the texture of concrete versus formwork. It was purely judging based on geometry. And again, if you have severely occluded components that on the job site happen a lot, you're going to have other examples of issues. So over time, we thought, well, maybe we can go back to more computer vision and look into visual appearances that we have in image and understand what is it that we see. I want to show you an example of a very simple foundation wall. If you have a foundation wall, the stages that you have in construction are placing formwork, reinforcing it, placing concrete, finishing the surface. If it's exposed, you're going to do cladding. Otherwise, you're going to do waterproofing, water membrane, insulation, and backfilling. We need to learn every one of these representations on the job site. Two problems. In construction body of knowledge, nobody's actually formalized these sequences. Clearly, it doesn't exist. The only person who's done it is Diego Echeverri, 1998, University of Illinois. He did his PhD here, way before I was also a student here. And it's the only publication that we have on formalizing these sequences from a data perspective. And two, where are we going to get the data to train these models? Also, I've already mentioned about many problems that we have in the design, but when we design a wall, we only show a box in design. We don't actually model the layers that you should be expecting to be detected. What do we do instead? We use metadata to represent these types of data. And of course, the scheduling, there's a lot of art than science in the world of scheduling. So that makes this process more complicated. Again, I don't intend to get into details. The first step that we decided to do is to take what is now done with deep learning. At the time, this is prior to deep learning. So you see, this is our first algorithm in 2014. The idea was that we would create our own convolutional layers. This was actually 48 layers. And we vector quantize representations that we get from different textures. And then we feed into some supervised classification process to learn a model that can say brick versus non-brick. And we can extend it to a multi-class classification. And we publish a number of journal papers on this, on how this works in construction. But then when you do this repeatedly, you realize that, again, there will be more opportunities for you to take things that you're learning in civil engineering into the world of computer vision. We changed the way of thinking about material recognition, and we created an algorithm called geometry-informed recognition. This is a CVPR paper. The gist of it is really simple. When you look into asphalt, do you expect to see asphalt on a vertical structure? No. You expect to see that on the horizontal structure, right? That knowledge alone can actually minimize significant amount of confusion that these algorithms have on differentiating one texture against the other. So what we're basically doing is that macro texture and micro texture is being modeled. I'm not going to get into the details. Instead of blindly applying deep learning, we actually took the last layer of deep learning, and instead of using a logistic regression, for those of you who use that, we actually decided to use supervised support vector machine, mostly because you can easily fit the hyperplane that would differentiate these models. And for the first time, we actually showed that the way people have been thinking about material recognition in world of computer vision can be enhanced by geometry, because nobody is designed randomly in the built environment. Everything is designed based on geometry. And a data set, for those of you who might be interested, the entire code is something that we've publicly made available. And this is the last piece of work to kind of showcase for you how we bring concepts from theory into the practice. The more we put these visuals and color codings in front of people, the more we learn that people come back to us and say, hey, can you tell me how I'm supposed to be revising a schedule? Because our only solution is throwing more body at work and get more work done, which is not what we promote. You can change the sequence of the work, you can change your location, you can change many, many factors. So we delve a little bit into some natural language processing and vision models to automatically learn best practices of planning and use that as a base of planning. So there's a number of new publications that we have on that front for those of you who might be interested. So I want to summarize what I've shown you so far. There are 4 use cases. You take the visual data, you can track progress. You can use that as a base of quality control. You can verify payments. And down the road, you can use that for liability purposes. And when you start thinking about it practically, it's no longer just precision recall. The dynamic of people thinking about the solution completely changes from the moment that you present it to them as a professor versus selling that solution to them. The value proposition is totally different. So you need to make things that are more understandable by someone who's on the job site. What are those items? Cost and time. Those are the only 2 metrics, okay? Now, between cost and time, there are things that are more tangible and things that are not tangible. And if you want to sell it, that differentiation becomes important too. The number 1 reason that people buy our software is because they don't want to walk on the job site. They want to minimize travel time. That sells for itself. What else? You can obviously do quality control. If you self-perform, there's a lot of value. If you have subcontractors that may file lawsuit against you, you can save that lawsuit. This is actually on a General Motors facility. And of course, you can save your time by doing more quality control. And on scheduling, there are a number of other things that we've done. I want to bring it back to things that we typically don't do. Many of us, we work on interdisciplinary problems. And from time to time, our thinking is we're going to be adapting these algorithms that we have in machine learning, computer vision, so we can make a contribution to body of knowledge in civil engineering, which is a great goal in itself. But there are many, many moments that you can actually take knowledge from our own area and feed it back into the world of AI. And I showed you a few examples. I showed you how you can bring the concept of design, improving reconstruction practices. I only touched on geometry and a little bit of semantics. I didn't get a chance to explain interdependency that we have between the components. And again, here, you can flip the coin and start thinking about it from a different perspective. There's a lot that you can explore, especially for those of you in this audience, because you actually work from a design perspective. Everything in design can be used as a base of training, things we want to detect from the real world. Whether you are looking to it from a condition assessment perspective or construction, everything is driven by design. So we can generate synthetic data and actually share that data so people can actually build on our own data sets too. I also want to caution you that this cycle is not the same. We can always publish by bringing these algorithms into our own domain, but the cycle of actually taking ideas from our own domain and pushing it back into computer vision, maybe every 4, every 5 years, if you do that, you're actually helping those people to understand that their word of, using computer vision in the wild can be adapted to a domain specific and be adapted for new use cases. So I'm not going to touch on ongoing research. I know I'm almost at time. I just want to wrap up to say, obviously, there's an army of people that have been behind this work that have made this happen. There's an army of people that support implementation of this technology across job sites, and they've all been part of this journey. I'd be happy to take any questions, comments you have on the engineering side of it, on the technical side of it, on the scientific part of it.
Thank you all so much, and thank you, Professor Golparvar-Fard, for such an amazing presentations. We're only going to be able to take 2 quick questions due to time constraints, so let's start with a round of questions. Go ahead.
Thanks, Manny. This was great. It brought back a lot of memories for me too, because I think the last time I watched you deliver a lecture for an hour was when I was a student. So I was sitting in your class. So this was great, and actually, then it brought back the memories of when I did an internship for a big general contractor. And they put me originally in the estimating office, which was a very interesting role. And I got the sense that the estimator's job ends the day that the project is awarded, basically. You win the work and then you pass it off to the team that's actually going to build it. But I wonder how much of this data, because maybe that's one reason, at least in my mind, why a lot of projects are falling over budget, because the estimator was trying to win the project and maybe didn't have the best data informing what their estimate was. So how much is this kind of data that you're capturing while the project's going on and after it's built, contributing, feeding back to actually the bidding process?
It's a really, really good question, Ramesh. Thank you for reminding me. And I'm happy we've had the opportunity for working together for many years now. Let me go back to what I showed before on bringing data back and missing the feedback loop. So we've not been able to do a whole lot on the quantity side. We've done more of it on the timeline perspective by being able to make more realistic schedules. On the quantity side of it, you saw the examples I was showing you from Shimizu. So I can only maybe name 2 or 3 projects out of these thousands of projects that people have actually taken the action of bringing that data. Problem is the people who do the estimation are not the ones who execute the job site, right? So I go back to the same coordination I was mentioning before. One way of addressing that problem is through what we call BIM execution plan. That means you actually put together an execution plan of who should do what part at what point in time in the project, and that needs to be sponsored and paid for by the owner. So the number of owners in the US that actually do that, but it's not even common in 2025. So from a concept perspective, it's doable. In practice, we still have long ways to go. Brown.
And we can take another more question.
Anything you didn't like or any concern? Yes.
Okay. Thank you so much, Professor. I have 2 small questions. The first one is, do the drones need to follow a design or planning path when collecting the data? And it's a trade-off between the image overlap and the accuracy and precision. And the second question is about, you also mentioned the texture descriptor.
Mm-hmm.
So I'm not sure it's a point cloud descriptor or text or image descriptor.
Got it.
Yes.
I'll be happy to answer those 2 questions. So one question is, the easiest one is on the feature side. It's purely image features. We actually always are looking to features from the image perspective. Over time, when we started this work, our idea was to use autonomous platforms to do the data capture. Truly, that's how even when we started the company. So the idea was that we can come with an algorithm that we can autonomously fly the drone. But then FAA put a regulation. Today, if you want to fly a drone, you need to have line of sight to the drone. And please don't make an attempt of doing that on campus. You're going to get a $150 fine if you don't coordinate that with the emergency management team on campus. Disclaimer for everyone in the session today. You typically have a number of problems. You end up doing a capture based on best practices. You have limited coverage. I've already mentioned about drift and resolution, the problem that you and I and Mohammed have been looking at recently. But the good news is that there are platforms that are coming out to the market. I've just only shown you 3 of them. Boston Dynamics is actually a partner to our company and the team. But before getting there, this is the problem you need to worry about. What are the means and metrics that you want to use to actually understand what defines a good capture? And to your point, this is actually a recent publication that we have that offers 6 different metrics. One of it is purely on reliability of feature track generation and computer vision. Some of them are more on the operation side. The capture gets checked for line of sight, for where the person stands, battery requirements. So part of it is multi-objective optimization, and part of it is satisfying technical requirements of accuracy and completeness. We actually brought that into the practice for bridge inspection too. This one, you don't have any design. There's no 3D design exists for bridge that you can check the quality. But we actually did a very smart strategy here. We took Google pictures, we crawled through them, we pay a service to do that. And we actually extract that data and we generate a 3D model based on existing photos. That model is not complete, that is not accurate, but it's good enough that we can create an initial flight plan that can be actually simulated and tested to satisfy these requirements before the person shows. Both of these works are recent publications that they can look into. Are people looking to more automation? Yes. The company I can refer to is the Skilled AI. Boston Dynamics, unfortunately, no. As much as we partner with them, the platform is $72,000. I want to show you back the picture again. This piece of laser scanner that sits on is roughly $100,000. So looking at $150,000 of investment, nobody lets the dog walk alone on the job site. You always have someone walk it because of the cost. Plus, they don't let you integrate with the SLAM algorithm runs on the platform. So you have to have an independent algorithm for scanning versus localization of the robot, which defeats the purpose of using the ground robot in the first place. So as much as it's interesting from a theory perspective, in practice, you have these limitations.
Thank you so much again.
My pleasure. Thank you.
Please, everybody join.